Hi guys, welcome back. I want to talk about a topic today that may sound really simple. It turns out it's really complicated. That's counting. I think if you think back to your youth or talk about, talk about math with little kids, one of the first things they learn is counting. This notion of matching up one to one with an object to some enumeration, right? And they might look around and you put some objects on a table, say 5 pennies. You'll ask them how many pennies they are, and they'll say 1, 2, 3, 4, 5. It's interesting, thousands and thousands and thousands of years ago, we didn't uh, necessarily have a lot of numbers. In fact, we used to say things like 1, 2, and then a few, or 1, 2, 3, and then many. After a certain number, we just thought of it as a lot. But as trading developed, and especially as things became monetized and we had this notion of currency, the need for counting became greater and greater. And it turns out that there's actually some very deep principles behind counting, and some of them can be actually quite complicated. So we're gonna start small here, and we're gonna build up. So let's take a look at what we got. Let's see here, come over here. So let's say that there's a game, and this game is played by selecting 3 objects. The first time you pick a letter, and then you roll a 6-sided dice, and then you toss a coin. How many different outcomes are possible? Well, let's think about this. You could have the letter A, right? Let's see here, I'm gonna go dark blue. You can start with the letter A, right? That could be the letter you pick. Wait, what's going on here? Okay. And then from that letter A, you would have the dice, right? 1, 2, 3, 4, 5, 6. Let me actually do this. And then each of these is going to have 2 choices, right? Heads or tails, heads or tails, and so on. In fact, so if I were to list them out, I might have heads, A1 heads. That's an option. A1 tails. That's an option. A2 heads. That's an option. A2 tails. That's an option. And so you can see what I've done here. I've sort of held the A constant and then held the dice number constant, and then gone through the choices on the coin. Well, if I were to list these out, that's going to be a lot, right? I mean, if I kept going, what would the next one be? Let's see. A3 heads. A3 tails. And I'm only halfway through the dice, not to mention the entire alphabet. So while I could list these out, and I could do it systematically, gosh, it seems like it would be nice if we could get our hands on some underlying principle that we might be able to employ. So in the spirit of George Polya, let's back this up and start with something a little simpler. And by simpler, I mean just easier to count. Let's say instead of that complicated game, we're simply tossing a coin and rolling a dice. How many different outcomes are possible? Well, let's list these. So if I'm tossing a coin, I could get heads or tails, right? So if I'm also rolling a dice, I could get numbers 1 through 6. So my possibilities would be heads and 1, heads and 2, heads and 3, heads and 4, heads and 5, heads and 6. Or we could play the case where the coin is tails and have tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. Now, you can convince yourself fairly easily that this is all possibilities, right? One of these things will happen. Don't be that person that says, oh, the coin can land on its edge. We're going to assume that never happens. So this is it. You toss a coin, you're getting heads or tails. You roll a dice, you're going to get 1, 2, 3, 4, 5, or 6. So together, one of those things will happen. So how many different outcomes are possible? Well, let's count them. 12. 12 different outcomes are possible. Okay. Let's get it a little bit more complicated. Suppose a new car has the following options. 3 different colors. I'm sorry. Let me fix this here. All right. So we got these 4 different colors: white, black, green, or silver. And we've got one of 3 different trims: EX, LX, or LTD. And then the 2 engine options: a standard V6 or a hybrid engine. So we have some options, and we want to count, right? We want to know how many total different car options are available. So what I'm going to do is I'm going to build sort of a tree here. I'm going to say, okay, let's start with my colors. I've got white. Whoops. I've got white. Now, from white, I have some options. I have EX, LX, or LTD. And from each of these, I have some options, right? V6, hybrid, V6, hybrid, V6, hybrid, okay? Now, another choice would be, what are my colors? White, black. So if I have black, again, EX, LX, LTD, V6 or hybrid, V6 or hybrid, V6 or hybrid. And then I keep going, right? I could say, okay, well, what if I have green? Well, for green, again, I could have the EX, the LX, the LTD. And for each of these choices, V6 or hybrid, V6 or hybrid, V6 or hybrid. And then lastly, what's my last color choice? Silver? So silver, EX, LX, LTD, V6 or hybrid, V6 or hybrid, V6 or hybrid. And so each one of these endpoints to these branches represents a car option, right? It's going to end with either a V6 or a hybrid. So if I count these up, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Whoops. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 24 different possible outcomes. Well, let's think about this. You know, this isn't necessarily a difficult process once you understand just the mechanics of organizing your tree branches, but still, it seems kind of clumsy to have to literally point and go 1, 2, 3, 4, 5, right? That doesn't seem like a very sophisticated way of doing things. So can we pull out some patterns? Well, let's look at our first example. In our first example, we were looking at, we had 12 outcomes, right? Well, we're looking at the dice and the coin, right? How many different outcomes for the coin? Well, heads or tails. Two different outcomes. And what about the dice? How many different outcomes for the dice? 1, 2, 3, 4, 5, or 6? 6 different outcomes. So we had 12 total. The coin was 2 by itself. The dice was 6 by itself. 2 times 6 equals 12. Huh. Well, let's see if this works out for example 2. All right, in example 2, we had 24 outcomes. Well, color. How many options? 4, right? Trim. 3. Engine. 2. What's 4 times 3 times 2? Oh, help if I actually can do it correctly. But yeah, 4 times 3 times 2? 24. Interesting. So it seems that if I want to know the total number of outcomes, I can just look at the individual events and figure out how many outcomes those have by themselves and find the product. And that is precisely right. That is what's known as the fundamental counting principle. Okay? It says if event A can happen M different ways, and event B can happen in different ways, then the number of ways A and B can occur is M times N. And this can be extended to any number of events. Okay? And events, think outcomes. Okay? If the outcomes, if A has M different outcomes, if you want to think of it that way. So you just multiply. How convenient. And what we've just stumbled upon is the study of counting, known as combinatorics. It's a study of counting and arrangements, or how many different arrangements. And so I used some language, some terminology that you may not be familiar with yet in my discussion of the fundamental counting principle, namely the word event. Well, an event is just an outcome of some experiment or game. So, for example, tossing a coin. Heads is an event, right? You can get heads. Tails is an event. Okay. If I am, say, picking a horse to win the Kentucky Derby, if that would be an event, it's an outcome that can occur, whatever horse I pick. How about forming a jury pool? An event would be a jury pool with equal representation of male and female. A little more complicated an example, but of all the different jury pools that could be formed, this would be one of those. And every forming of a jury pool is an event. Okay. Now, the set of all possible events or outcomes is called the sample space. Okay, the sample space. Excuse me. And so really, in the first two examples, the coin and the dice, and the car with the different colors, trim, and engine type, in those first two examples, we found sample spaces. Okay. So let's find the sample space for tossing two coins. Well, it's a set. And what could the outcomes be? Well, heads, 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 tails, tails, heads, or tails, tails. That would be a sample space. Okay. About B? Tossing two dice. This one might be a little bit more complicated, but you could have 1, 2. I'm sorry, let me start more intuitively than that. You could have 1, 1, 1, 2. And again, this is not the number 11 and 12. This is 1 and 1, 1 and 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, 3, 2, and you get the point, right? We could list those out, okay? If you want to finish listing them out, I'll tell you there's 36 total, okay? So let's go back to our motivation problem, right? It looks to me like there are 3 events. Picking a letter, rolling a dice, and tossing a coin. Well, picking a letter has how many different outcomes? Well, for a Hawaiian alphabet, it'd be 14. It's not the Hawaiian alphabet. We're going to assume the 26-letter English alphabet. So picking a letter has 26 outcomes. Rolling a dice has 6 outcomes. Tossing a coin has 2 outcomes. And so the fundamental counting principle, FCP, tells me the total number of different outcomes is 26 times 6 times 2. Okay, whatever that is. Let's see here. Come over to a calculator. 312. Okay. Now, is that something you really wanted to list? 312 different outcomes? No. But it's nice to have this fundamental counting principle. Okay. And so we want to be comfortable using this fundamental counting principle. And as we move forward, we're going to do just that. You're going to see this thing at play in so many different ways. But for now, what we want to be able to focus on are the following three very simple things. Number one, identifying sample space, being able to determine how many elements are in it, understanding what events or outcomes are, and then applying the fundamental counting principle to find the total number of ways multiple things can happen. I would encourage you to move back and forth between listing things out and observing the fundamental counting principle. I mean, you don't necessarily have to finish listing things out, but you can see it at play, right? If I come back up here, say to this example, right? You see it at play here because we've got, right, the colors. There are 4 different colors. There's 4, and each of those branched off into 3 different trims, and each of the 3 different trims branched off into 2 different engine types. And so you see the 4 times 3 times 6, right? I've got 4 options for that first. If I want to, I could even generalize this a little bit. You can say, okay, I had 4 options there, and then I had 3 options for the next spot, and then I had 2 options for the last spot, okay, in terms of my branches. So, all right, so I would encourage you to go back over this. Again, make it your own. Rework my examples. Make up your own. See what would happen. Play this again, but say, you know, finish writing the sample space for 2 dice being tossed. The more you play with it, the more this theoretical fundamental counting principle is going to start to look just more and more clear, even obvious through your counting methods. And when that happens, you're really building intuition, and there's no substitute for that. So please do spend some time digesting this, and then we will move on to the next. Remember, we're studying combinatorics, counting and arrangements. So arrangements are on the horizon, and there will be some fascinating discussions there. So enjoy this, and I will see you soon.